Hello, everyone. So today I'm unable to attend physics club due to my individual sophomore student meeting with my counselor. So I made this resource for you guys to follow along. Today we're discussing continuous mass transfer in our lesson of mechanics with space applications. So what is CMT? It's where mass is being ejected from a source, right? So you can see on the right, you have this rocket which is ejecting fuel. And so that's what causes the force of thrust. That creates force of thrust, which counteracts the force of gravity or force of weight. Right? Two of the other forces in flight are lift and drag, which are negligible. We will talk a little bit about them later. Now, our system is going to be our rocket and fuel, right? So we'll do a mathematical analysis of some of these key ideas using our rocket fuel system. So here's some key ideas. At time t, here's the rocket. By definition of momentum, we have that it's equal to mass times velocity. Right, so here you have momentum at time t is mass of rocket times the velocity of rocket at time t. At time t plus delta t, you have the momentum of the rocket again, which is mass times velocity at time t plus delta t. But you also have the fuel, right? Because you have the system of rocket and fuel. So from the fuel, you have this contribution of delta m sub f, the mass of the fuel, times the velocity of the fuel over here. Right? And so to create the momentum expression, we have to add these two terms, right? And this is exactly what we do over here. See, here's the rocket term. Rocket. There's the fuel term. One common misconception is that this fuel term is acting downwards, right? Actually, in the ground reference frame, it's acting upwards, right? In the reference frame of the rocket, it's going downward, right? So relative to the rocket, it's going away from the rocket, right? But in the ground reference frame, it's actually moving upwards. So let's elaborate on that. We have this velocity u, which is the velocity of the fuel relative to the rocket. Remember that because it's important to the derivation. Right? So it's the velocity of the fuel in the reference frame of the rocket. So let's look at that. This is the rocket reference frame. This is the rocket reference frame. Right? And the V fuel over here is actually in the ground reference frame, right? How do we relate these two quantities? Well, you have to add in the velocity of the rocket at time t plus delta t, right? So it's a great example of this. Let's say, for example, I'm running forward at 5 meters per second. And then I throw the ball behind me at 2 meters per second, right? Well, relative to me, in my reference frame, the ball is moving 2 meters per second, right? Away from me, backward, right? But relative to the ground reference frame, the ball is actually moving 5 minus 2 or 3 meters per second forward, right? In the ground reference frame. So this is exactly the same concept over here, right? Where you have the addition of velocities between different reference frames, right? And so that goes back to the idea that the fuel is actually moving upward because you're adding this contribution here. Note that this equation is not a signed equation, right? So u is actually a negative term if you create a coordinate system where j hat is upwards, right? And u becomes negative term, which we'll cover later, right? But as of now, it's just vectors, so we're just adding the vectors to show the addition of velocities. So keep in mind our momentum expression from before. We're going to make some simplifications. So this is shorthand right here. M sub r of t is m sub r. And then here you have m sub r of t plus delta t. You can just express that as m sub r of t plus delta m sub r, right? It's just a change in the mass of the rocket plus the mass of the rocket, right? And so again, this is unsigned stuff right now. And so after that, so you just use the shorthand from here to here. And then after that, we have that delta m sub f is equal to negative delta m sub r. This is just saying that the rocket is just losing the fuel, right? So the fuel is exiting from the rocket, right? So if the rocket is like losing mass, and then like their fuel is, you're gaining some fuel mass, right? If you consider the rocket and the fuel, right? So this is just that. It's pretty obvious once you think about it, right? So this is the original momentum expression. And now we have this new momentum expression. Where did this come from? Well, you see this m sub r plus delta m sub r term over here. That came from this m sub r t plus delta t and this simplification over here, right? Then you have this delta m sub f term, right? Which we use this simplification over here, and you get negative delta m sub r over here, right? And whereas this is just your v sub fuel, right? We're covering it back here, your v sub fuel over here. Substitute that in here, you get that. So I'm just putting the pieces together, right? Here's our momentum at time t plus delta t. And why did we compute this? Momentum at t plus delta t and momentum at t. Why did we compute that? Because of this right here, right? You have your momentum principle. Force external is the derivative of momentum with respect to time. This is actually a formulation of Newton's second law, kind of. And so using some calculus, right? So this is with calculus limit definition of the derivative, which we're applying over here. And so I'll assume that you know that. If not, Google it. And so we substitute in the quantities, right, of our momentum that we calculated, t plus delta t and momentum at time t. We substitute them in, and then we have this cancellation, right? If you look carefully, you have that this term over here cancels out, right? It's your m sub r times v, your delta m sub r times v sub r of t plus delta t, right? That term is canceling out if you look really carefully on those parts of the expression, right? And then you have this over here, you have this m sub r times v sub r of t contribution, right? This negative, you subtract that there, right? And so the group terms, this is like a delta v sub r term over here, right? So you have m sub r times this kind of delta v sub r you can see over here over the delta t. And then you also borrow this term over here and move it like there, right? Next step, so you have this delta v sub r term over delta t. We take limit as delta t goes to 0. You have calculus here. It becomes the derivative of the velocity of the rocket with respect to time. And then over here, you have your delta m sub r over delta t term, limit as delta t goes to 0. This becomes your derivative of the mass of the rocket with respect to time, right? And so, and this is your force external, by the way. I didn't write it so many times. I started adding it over here. Next, we're just going to transfer this term over here to the left-hand side. We're going to add it to both sides. This is on the left-hand side. Now, let's keep track of what we've been doing here. This is actually the thrust term right here, right? This is because that rocket is ejecting fuel. You get this thrust term over here. Very key concept. From force external, you can put in external forces like gravity. But you can also add in forms like forces like drag and lift afterwards, which can factor into these force external. But those are a bit negligible. For now, we're working on gravity. I guess we can focus on the gravity term. And this is just mass times acceleration, Newton's second law extension of that. So let's go to over here now. We have our equation that we were working with before. This is the same as what we had back down there, right? And so the next step over here is you consider the system as just being the rocket, right? And so what we do here is we make simplifications, right? We talked about how this is the force of thrust over here, and how the force of thrust is just negative derivative of the mass of the fluid with respect to time times the u over here, which you remember what the definition of u is, right? U is the velocity of the fuel in the rocket reference frame, right? Over here, by the way, sorry, I was confused for a second there. This is the negative sign, right? So remember how we were talking about m sub r equals the negative delta m sub f, right? Or delta m sub f is equal to negative delta m sub r. This is just that right here. You can see over there. It's a bit hard to see sometimes. MR over here, you have the MF over here. So that was just a conversion from this step that we made, right? It's just that, basically. Yeah, so this is just the force of thrust, right? That we identified in the expression that we mentioned before. And this is equal to the negative derivative of mass of fuel with respect to time times u. And so this, know what we did over here, like where did the negative go, right? What we did was we turned this vector into a scalar, right? So this is where, sorry about that, I have low battery, guys. So u over here, the vector is equal to negative u times j hat, right? Because it's a negative quantity actually. If you take up to the positive direction, it becomes negative quantity because it's the velocity of fuel in the rocket reference frame. Then you have gravity, of course, acting downward, which is our force external that we're considering. Next, we can put all these together and get this rocket equation. This is the alpha stage of rocket equation. We'll do a few more changes and then we'll finish. But this is the basic rocket equation with our gravity term and our thrust term, right? Afterwards, we have to derive it for a specific case. Let's look at a specific. Let's look at a visualization. Sorry, guys. We have our momentum at time t, right? Is just the mass times the velocity, and then some time dt passes, right? T plus dt, infinitesimal time, and you get this dm contribution and this dv contribution. So we use area of rectangle here. This is mdv. This is vdm. Let's add it in. dp, which is our infinitesimal momentum, is equal to mdv plus vdm. We'll divide out dt on both sides. There we go. And so you get that your force, remember the momentum principle, force momentum principle, is equal to this m, this correlates to this, and then this is just v is minus u, right? So you get m mass of rocket times derivative of the velocity of rocket with respect to time, minus derivative of mass of rocket with respect to time, times the u. Remember our quantity u from before? And so that is just applying this formula over here, right? And so this is a cool visualization. This is just additional speculation on what we had before. Maybe like a shortcut kind of help you remember the formula, but also a very cool idea, right? Let's finish up now. We had some of our terms from before, what we were working with from before. Next, what we're going to do is we're going to divide out dt, multiply. We're going to multiply through by dt. Sorry about that, guys. We're going to multiply through by dt on the next step, and then divide out by m sub r. So this is multiplying here. Here we're dividing out the m sub r, right? And then we can integrate on both sides from the initial to final. So first on the left, far left, we integrate from initial time to final time, you get this, right? Using some basic calculus. Next, you want to integrate the d m sub r over m sub r, right? From the initial mass to the final mass, you get this. Where did that come from? You know calculus. You have really cool idea that the integral of 1 over x dx is the natural log of the absolute value of x, for example, right? And so from there, you just evaluate it at the initial mass and the final mass, right? If you do it with the mass instead. And u is like a constant here now, right? All right, and then you just integrate from the initial velocity to final velocity to get that. Next, we're going to impose some initial conditions at time t is equal to 0, the time initial. You have that your total mass is just the mass of the rocket plus the mass of the fuel in our rocket, if we're just considering the rocket to be the system, right? And then at our time final, we have that the mass final is just the dry mass of the rocket, right? The mr comma d right there is just the dry mass of the rocket, right? And so here you can have your initial velocity and final velocity as well, right? We're just saying that the rocket starts from rest. Rocket starts from rest over here. Anyways, we make the simplification, negative g t sub f plus u natural log. So that this equation right here is just simplified from the one you see above. This is like the final rocket equation, right? And this is the key rocket equation right here. This is what we were aiming for. So this key result of this, you want to minimize this term right here. This is minimize. You want to minimize this term right here. And that's by making the shortest burn time, right? You want to drop t sub f so that this negative gt sub f term gets smaller and smaller, right? So that's why you want a very short burn time so that you can have the largest velocity to get into orbit when all your fuel is burned. So next we'll look at this question of how much does it cost to send a person to space? Just place your bet, think about this question, maybe do some research or just think very deeply using the rocket equation as to how much can it cost to send a person to space? Like maybe like make an estimate or something, right? You can do like different rockets like Falcon and SpaceX, and then the different rockets, right? You can do some research on that. And so next you have the drag forces, which is just any friction force in like a fluid. It's like air can be a fluid, for example, or just like a liquid, for example, right? So this is literally just any force that's resisting motion in a fluid. So that can be like a viscous force. It can be like air resistance, right? It's generally defined as 1/2 rho v squared plus drag coefficient times cross-sectional area. For example, the cross-sectional area part makes sense, right? If you have like really high cross-sectional area, then you have more air resistance, right? And then you have like smaller cross-sectional area, means you have very low air resistance. So that's a pretty cool idea. So you think about like running, for example, you think about like your track runner trying to minimize his or her air resistance, right? By leaning forward, you have your track runner doing that, trying to improve the run times, of course. And then you have your Reynolds number right here, which basically tells you about laminar and turbulent fluid flow. We'll cover more about it next time. But it's basically defined to be the density times the flow speed times the characteristic linear dimensions. This could be like a diameter. Like for example, for the tubing of a pump, you could have diameter in many applications. You have, it's generally called characteristic linear dimension, depending on your application, right? And so you have Reynolds number, which is your density times your flow speed times your characteristic linear dimension divided by your dynamic viscosity of the fluid. And so you have this equation right here. And then, so if you have low Reynolds number, that is laminar. If you have high Reynolds number, then that is turbulent. And so your Reynolds critical, you could say, is like a critical Reynolds number would be 2000, right? Anything below 2000 is laminar, anything 2000 or above is turbulent. And here's a cool visualization of a sphere right here. And you can have some turbulent eddies right here, and then the currents, right? Here you can have them in like air or in water, or you can have like a different turbulent fluid flows. Right? Like in a jet engine, you can have a turbulent fluid flow, for example. Let's discuss angular momentum. Angular momentum is the rotational analog of linear momentum. And so, for example, a planet has angular momentum, right? Think about the Earth. The Earth is rotating around the sun, right? It's going around the sun in orbit. That's its orbital angular momentum right there. And it's revolving in place as well, right? You learn this in like the elementary school, right? So that's spin angular momentum right there. And the fact that the planet rotates and revolves is elementary idea. Then you have the different types of angular momentum there, right? So your orbital angular momentum is just r cross m. It's r cross p, which is r cross. This is r cross radius cross momentum, right? It's a cross product using your pre-calculus ideas, right? So you have your r cross mv, and then you wanna, and then you have the spin term, right? So you have this moment of inertia times angular velocity term, which is your spin angular momentum that you see over here, right? Is this term. So next you can see how we do like a vector addition of these terms when you're thinking of the planet, right? You have your orbital spin angular momentum. You can see the vectors of momentum, linear momentum vector, and like a radial vector, and other quantities here. Your moment of inertia and your angular velocity vector, right? This is the angular velocity over here. Anyways. So so this is the angular momentum vector over here, and this is your angular velocity vector. All right. Let's continue. So total angular momentum is orbital angular momentum plus spin angular momentum. You can have a vector addition right here. Here's orbital, here's spin, and then here we add them to the total angular momentum using vector addition principles. All right, from here we'll end out. Hope you guys learned something. Hope you guys enjoyed this, and we'll see you next week. If you have any questions, you can use Discord, or you can email bchsphysics@gmail.com, or you can even email me, rohan.sachdeva@warriorlife.net. And yeah, I look forward to discussing these principles with you. Thank you so much for listening, everyone, and have a nice day.